way below functions, and that means a K in O, which is inside U and it's pre-compact. So if you take any such K, then you can get a bisection B whose source contains K and whose range is inside V. So if I have this picture in the unit space, I have two sets U and V. These are where the characteristic functions are supported. So I say U is dynamically below V if I take any pre-compact subset inside U, then there exists some bisection B, which is in my inverse semigroup basis, that sucks in K and blurts out something inside V. Yeah, so here I've denoted denoted K1 in the range of B in as squares because they're pre-compact, but and something to note is that the source of B need not be exactly K, it just needs to contain K, and the range can be anything, we don't have to worry about it. And if we can do this for every pre-compact set inside U, then we say U is dynamically below V. And since F and G's are finite sums of characteristic functions like this, then if you can do this for all those sets in the support, then yes, then it's dynamically below.
Sorry, Akshara. So
Yes.
don't you want this K to be contained with the closure in the set U?
Wait, no, that is
Because
also
compact alignment, compact containment means that K is pre-compact and the closure of K is contained in U.
No, because in the way below, what I have here is just that the support of G is compact. Just give me a second. And the Hausdorff case, yeah, okay. Yeah, thank you. Yes, then the square makes even more sense. Yeah, thank you. Yeah, so K bar, so the closure of K should be in U. So if you can do this for all case pre-compact case inside U such that its closure is inside U, and you can, and there are bisections in B that take this and send it to something inside V, and you can do this for all sets in F and in F, then you have dynamically below relation. So as you can see, this is not just normal domination, it's not just pointwise domination, but there's this dynamics of the groupoid coming into the picture. And if dynamically this is true, then we have this relation. So the type semigroup is just f of O quotiented out by the equivalence relation that comes out from this dynamically below relation. So the dynamically below relation is a pre-order, and you take its equivalence classes and then you quotient out f of O with it. Then that's the type semigroup, and this will be an ordered monoid. And yeah, the order and the sum is as I've shown here. Okay, so now that the definition of the type semigroup is out of the way, I can go about relating ideas and states of the group or sister algebra to.
Sorry,
yeah.
So my Zoom crashed down, and I missed the definition of FO. And so it wasn't recorded, so it's better if it appears so that when people look at it. Characteristic functions on the use.
So yeah, it's just
okay. Your bisections are not necessarily compact. So your groupoid is not necessarily ample.
Exactly.
Okay, because if it had been compact, then the question about containing the pre-compact or its closure would have been the same.
Exactly.
Okay.
That's a good question, and I will talk about this more throughout the talk. Some of our results and examples, when we restrict to the ample case, it becomes easier and it becomes easier to see, and we have direct results. But our work is more general, and as you noticed, we do not even restrict to Hausdorff groupoids. So there has been previous work.
But the X is assumed to be Hausdorff.
Yes, the unit space is locally compact Hausdorff.
Yeah.
The space, the whole groupoid is not.
Okay.
That's the assumption, and I also assume it are, of course.
Yeah.
Yes.
Okay. Thanks.
Okay. So getting back now, let's relate ideals. So I define what an ideal is in a type semigroup. So it's a submonoid such that if there's a G in I, then everything that is dynamically below G is also in I. So this is an ideal with respect to the order. So it's also called an order ideal. This definition also exists in the generality of pre-ordered abelian monads. That's how we define it as well. But for the sake of this talk, it's enough if we work with type semigroups. Okay. Now, if you take a function f and you take all the functions that are way below it, this actually forms a directed set with a supremum f. And what I mean by regularity here is that regularity respects this supremum under way below. So
sorry
yes.
to bother you again, but wasn't this relation in SB of G?
Mm-hmm.
Didn't the preorder relation become equivalence?
Yes.
So yeah.
Yeah, it's
So
an
what does
order here. Mhm. It's not a total order. It's just an order. You still have
okay?
elements
Uh-huh.
dynamically below it. Like
Okay.
you still have elements that are dominated by
But
other elements.
but I mean the equivalence relation. F is equivalent to
Mhm.
G. Didn't it mean that F? So by the
Yes.
equivalence relation, you meant F less than G and G less than F.
Yes.
Okay,
Maybe I should have been
not
clearer
just
about that.
forget
No,
about
not
the
the
order
whatever. Yes.
and make
By
it
equivalence, I mean F
indefinite.
less than G and G less than F. Then they're
Okay,
thought to be
okay,
the same in the type
okay,
semigroup.
okay. Now I
Okay.
understand. Sorry.
Yeah. My bad. Maybe I should have been clearer. Okay. So getting back to ideals, I say that an ideal is regular if you take any f in the type semigroup and all the functions which are way below it are in the ideal, then this function also is in the ideal. Then it is called regular. So it respects supremum under way below. So as Willie pointed out, ample groupoids. So if you take ample groupoids, you don't have to worry about this way below because every set will be way below itself. So it's compactly contained. So every function will be way below itself. So in the case of ample groupoids, you can take B to be all the compact open bisections. Then O will be the set of compact open subsets in the unit space. Then every ideal will be regular. So in the ample case, it's easier. And is it true that all ideals are regular? No. So if you take a groupoid with the unit space as natural numbers with the discrete topology, and if you take O to consist of all finite subsets in the space N, then if you take the submonoid of f of O spanned by all of these functions supported on U's for finite U, then it is not regular because we want O to be closed under finite unions, not infinite unions. So if you take supremum of all such finite U's, then you get the whole set N, which is not in O. So every ideal need not be regular. Okay, now how do we relate this to ideals of a sister algebra? We know that if a group or sister algebra is simple, then its groupoid is minimal. So we relate ideals of the type semigroup to open invariant subsets of the groupoid, and this is the result. So if I assume that O has only pre-compact subsets, then it's equivalent that the type semigroup is simple, that is, there are no non-trivial ideals, which is the same as it having no non-trivial regular ideals, which is the same as the groupoid being minimal, that is, it has no open G invariant subsets. And we have a bijection between regular ideals and open G invariant subsets. So if I take an ideal I, then it corresponds to a G-invariant subset, which is the union of all the supports of F, which is present in I. And if you take an open G-invariant subset U, then the regular ideal that corresponds to it is the one generated by all the V's in O which are contained in U. So all the open subsets in the unit space that are inside U, you take them and you take the ideal generated by it. That will be a regular ideal. So this correspondence is true even without assuming precompactness on subsets of O on elements in O. But to get to ideals from regular ideals, we need the precompactness assumption, and this is actually needed for our later results. Okay, now let's get to states. So we want states and traces on the groupoid sister algebra. As you saw earlier, I talked about traces when getting the dichotomy, when talking about the dichotomy. So I also define a state on the type semigroup. It is an additive order preserving map nu to closed zero infinity, such that it is 0 at 0, or equivalently it's not infinite everywhere. So the last condition is just so that it's not a stupid additive order preserving map. And similarly, as for ideals, I also have regularity for states, which is the same that it respects supremum under way below. And again, looking at the ample case, if O is a set of all compact open subsets, then every state is regular. And if you're outside the ample case, or in any setting, every state actually induces a regular state, and that is by this formula here. So if you take a simple function 1u, then the image of the regular state, the induced regular state, is the supremum of all the images of 1v, where v bar is subset of u. And here I have made sure to write v closure, which I forgot earlier. Yes. So so yeah, every state induces a regular state, and the state is regular if and only if the regular state it induces is itself. And it can happen that the regular state induced by a non-trivial state is trivial, and this does not happen. That is, the induced regular state is non-trivial only when the sets in O are precompact and the unit space has finitely many open invariant subsets, which happens when it is minimal, for example. Okay, how do we relate these two states on the sister algebra? So there's a bijection between lower semi-continuous traces on the reduced sister algebra of the twisted groupoid, and G-invariant regular Borel measures on the unit space of the groupoid, and regular states on the type semigroup. And here we have a condition that the traces need to factor through E, where E is the canonical expectation from the reduced sister algebra to the Borel measurable functions on the unit space. And here we are considering B of x and not just C0 of x, because we are working in the generality of not necessarily Hausdorff groupoids. There, as we'll see later, we also need to look at the essential groupoid sister algebra, which is a quotient of the reduced sister algebra. And we'll need to use B of x because when you have a non-Hausdorff groupoids, you won't have many compactly contained continuous functions. You'll have it's better idea to take all Borel measurable functions. Okay, and what do the correspondences look like? So if I have a measure mu, the measure of a set U will be the image of under the state of 1U. And for a trace, tau of f will be integral of E of f with respect to the measure mu. So this is how these are related.
Small questions.
Mhm.
So the twist doesn't have any effect because the regular states are on SVG. I mean,
Sorry.
in one in the three bijectable sets, only one has an L in it. So it's the only one that where the twist appears.
Yes.
So the twist doesn't matter for the other two sets.
So if you have a twist on a groupoid, then there are even shear bisections on it, right? So you have even less ways to have the dynamically below relation. So that won't matter on the type semigroup.
So
Bartosz, you have a comment?
I think here it doesn't matter because here you consider
Yes.
only traces that are induced from, in fact, like B of X or C of X. So you only restrict to a certain class of traces. So these are not all traces, unless your groupoid is principal, and then all traces are of this form. So you don't describe all traces, just some nice class of traces that are induced from your union space. So that is why the twist doesn't matter.
Okay, thanks.
Thanks, Bartosz. Yes. Okay, so now that we related ideals and traces, we can combine these results and some other results that I did not show to you, and give characterizations of pure infiniteness and of stable finiteness for the reduced sister algebra. But before I go to that, in a lot of our results here, there was a lot of use of pre-order, like results on pre-ordered abelian monoids, and many of the statements we have is in the generality of pre-ordered abelian monoids and not just type semigroup. And there are some definitions from there which I'll need in my final statement. So, but most of you would know this, I assume. So in any pre-ordered abelian monoid, S as an element X is properly infinite if you can take two copies of it, and it still is dominated by the element itself. And if every element of the monoid is like this, then it's said to be purely infinite. And already from the name, as you can see, we'll relate pure infiniteness of the type semigroup to pure infiniteness of the groupoid sister algebra. And also, there's a definition of stable domination. So if you have two elements X and Y in a pre-ordered abelian monoid, and you take n plus 1 copies of X, and it is still under n copies of Y, then X is said to be stably dominated by Y. So this is sort of a paradoxicality that we have. So if the stable domination implies the usual domination for all pairs of elements in the monoid S, then it is said to be almost unperforated. So if X is stably dominated by Y, means X is less than or equal to Y for every X and Y in S, then S is almost unperforated. And this will be a condition in some of our results, which you can also recall is a condition for the Cuntz semigroup when we have results in sister algebras. Okay, now characterizations of pure infiniteness, one of the main results. So there's all these characterizations of pure infiniteness that it relates to there being no states on the type semigroup and the type semigroup being purely infinite, but it has all these conditions and it can look scary. So I'll just go through it and I'll give a simplified version as well. So this says that if the twisted groupoid is exact and it is residually topologically free, and the reduced and the essential sister algebras coincide. The essential sister algebra is, as I said earlier, a quotient of the reduced sister algebra, which we need to work with in the setting of non-Hausdorff groupoids. But if the groupoid is Hausdorff, then this is always true. The reduced and essential coincide. And I also assume that B consists of sigma compact bisections that trivialize the twist on L. And I write L here and not sigma, as many of you would have seen, because I use the Fell bundle picture. So Fell bundle is a sister algebraic bundle on the groupoid, and that is the same as a central groupoid extension, which we usually know of as twist of a groupoid. Now, there's also one of three conditions that the groupoid needs to satisfy. One is that X has finitely many G-invariant subsets, or O has compact open bisections, or that these compact subsets of O separate the G-invariant open subsets of X. Now, these conditions are of course satisfied if G is minimal, or if it is ample, and we take take B to be all open compact bisections. So this is a general result, but if we simplify, if we specialize to cases that many of us work with, then, for example, if G is twisted Hausdorff groupoid, which is minimal, then all those many scalar conditions that you see go away. But it's of course a specific statement of special version of the previous statement. And I assume that B consists of sigma compact bisections that trivialize the twist L. And if we take ample groupoids, of course, we can take B to be compact open bisections, and the sigma compact assumption also goes away. And I assume the type semigroup is almost unperforated, then I have an equivalence between all these statements. So the groupoid sister algebra is purely infinite. And this we know means that no hereditary sister subalgebra of the sister algebra admits a trivial state. And this is the same as saying there are no non-trivial regular Borel G invariant measures on X. If you recall from my first slide, I also said that the Banach-Tarski paradox, the border between the dichotomy for groups is that whether a measure exists or not. So these results are in spirit of what Tarski did as well. And this is equivalent to saying that the type semigroup SB of G is admitting no non-trivial state, which means, which is also the same as saying every non-zero element in the type semigroup is paradoxical. And what does paradoxical mean? It means that an element X is paradoxical if it stably dominates itself. That means there exists some natural number n such that you take n plus 1 copies of X, and it is still dominated by n copies of X. And this is the same as saying the monoid SB of G is purely infinite. That is, every element of it is properly infinite. So we have related pure infiniteness of the reduced sister algebra to pure infiniteness of the monoid under these conditions, which are not very restrictive. And the previous example, the one we have in the paper, is more general than this.
Sorry, a small question. Suppose your groupoid is a group. Does this apply? Because then the type semigroup will be classes of subsets of the unit space, which is trivial. So maybe it doesn't apply because it's not unperforated.
I think you forgot one more assumption. I think you want to assume that your groupoid is topologically free.
Yes, no, we just want it to be residually topologically free, right? And which is the case when
on this slide you have, but on the other one you don't have this assumption.
My bad. So the residually topologically free becomes topologically free when G is minimal, right? Yeah, which is what I missed. Yeah, I wanted to forget about residually, but I forgot all about topologically free as well. Thank you for pointing that out. Yes, so yeah, I hope that solves your question.
Okay.
Really?
Thanks.
Okay, so is Hausdorff topologically free and minimal, and type semigroup is almost unperforated, then we have this. Okay, so similarly, we have characterizations for stable finiteness. If the groupoid is has a inverse semigroup basis consisting of pre-compact, sigma-compact bisections that trivialize L, same as before. Here we have pre-compact as well. And if the sister algebra is simple, then we have these equivalences. So the reduced group or sister algebra is stably finite, which we know means it admits some faithful semi-finite lower semi-continuous trace. And this means that there are no paradoxical elements in the type semigroup, which if you know the GeNoCAS theorem, it's the same as saying an element is paradoxical if there are no states related to that element, right? So this is in the same spirit. So if no elements are paradoxical, that means there is some non-trivial state on the type semigroup, and that means there is some regular non-trivial state on the type semigroup, which is the same as saying there is a non-trivial regular Borel measure on the unit space, which is invariant under the dynamics of the groupoid. So these are the characterizations of stable finiteness and pure infiniteness. And we can combine this and we can get dichotomy results for group or sister algebras. And I'll show you one such sample result now. But I said that one of the conditions is almost unperforation, similar to what we have for the Cuntz semigroup. But many of our results actually do not require almost unperforation. A condition which is weaker than that often suffices. And the condition is this. So a monoid S is said to have plain paradoxes if every paradoxical element in S is properly infinite. So paradoxical element was that X is paradoxical if there exists some natural number n such that n plus 1 copies of it can still be arranged to be below n copies of it. Properly infinite means 2 copies of X is under 1 copy of X. So if this is the same for every paradoxical element, then we say that the monoid has plain paradoxes, and almost unperforation directly implies this. So using this sample result, we have combining the two previous results is that if I have any groupoid with an inverse semigroup basis of pre-compact, sigma-compact bisections, and the type semigroup has plain paradoxes, then if the group or sister algebra is simple, then it is either purely infinite or stably finite. So we just have the plain paradoxes assumption on the type semigroup and pre-compact, sigma-compact bisections on B, and we have the dichotomy in the simple case. Maybe I talk a bit about how the proof of this works, which uses some more monoid machinery. And so some papers by Rodam used results by Tarski in some generality, which Tarski did not prove in. And even these results in Rodam's paper were not in the full generality that we needed. So we prove this in an appendix in our paper, and I state this here. So if S is a pre-ordered abelian monoid, and you have elements X and Y in S, then when does Y stably dominate X? This happens if and only if, as far as states are concerned, the elements are dominated. So as far as states are concerned, so nu of X is less than nu of Y, and also X needs to be in the order ideal generated by Y. So in a monoid, if you take an element S, element Y, you take all the elements beneath it, and you take this multiples of Y and elements beneath them. That's the order ideal generated by Y, which I denote by this. So if X is in the order ideal of Y, and as far as nu are concerned, Y dominates X, then we say that Y stably dominates X. And this directly gives Tarski's theorem as we know it, which is an element y is not paradoxical if and only if there is a state nu that sends y to 1. So we get this as a corollary of what you call the Rodin-Tarski theorem. And from this, we have another corollary for any preordered abelian monad S. If it has plain paradoxes, then S either is purely infinite or it admits a non-trivial state. This, as you can see, it follows directly from Tarski's theorem. Yes. So if you combine this with the relation between states we have between type semigroup and sister algebras, we get this corollary here. That if the type semigroup has plain paradoxes, then if the sister algebra is simple, it's either purely infinite or stably finite. Okay, good. Any questions until now? Okay, nice. Then I do have some more minutes, a few more minutes to talk about an example. I was told to wrap up the talk in 50 minutes, and I think I'm on time. Okay. So we apply this to sister algebras that come from self-similar group actions on graphs. So this is work by Exel-Pardo, who wanted to generalize Katsura's algebras, which in turn generalize Kirchberg algebras and give a combinatorial picture of it. And they also generalize Nekrasovich algebras, which come from self-similar groups. And so Exel-Pardo algebras come from a self-similar action of a group gamma on a graph E. And the only assumption on the graph here is that it be row finite and it be directed and it has no sources. So the action is by graph automorphisms, and it is equipped with a restriction map. That is, if I take any GE, any pair GE for element G in gamma and an edge in the graph E, then you get an element G restricted to E in the group, and this should satisfy these two conditions here. So this is the self-similarity part of the action. And Exel-Pardo actually give a groupoid picture of sister algebras that come from this. They use inverse semigroups, and they define a tight semigroup for this action, and from that they get a groupoid. And the Exel-Pardo algebra, which you see here, actually is isomorphic to the group or sister algebra of that. So what's the Exel-Pardo sister algebra? It's the universal sister algebra generated by a bunch of elements. What are those elements? First of all, you get, for every vertex in the graph, you get a projection, and you get partial isometries for the edges, and you get unitaries for the elements in the group. And these needs, the isometries and projections need to be a Kuntz-Grigori family. That means that satisfy a similar condition as in the definition of a Kuntz algebra. And the unitaries need to be unitary representation of here I have said G, maybe I should have said gamma. Yes. And they need to satisfy these conditions. And the sister algebra you get by these elements satisfying these conditions is called the Exel-Pardo algebra. And here, as you can see, it depends on the graph E and the group gamma and the action between them. So this actually generalizes graph sister algebras as well as group sister algebras. So if you take the group to be just the trivial element, then you get a graph sister algebra. And if you mute the graph, you get a group sister algebra. Okay, and we have a dichotomy result for Exel-Pardo algebras as well as an example. So if it is simple, then we have these statements. So it's either stably finite or it's not purely infinite, in which case it would be 0 infinity. Here, G gamma E is the groupoid of the Exel-Pardo algebra, which I have not discussed here because it's a bit complicated. And yeah, so when a monoid is purely infinite. It is necessarily just zero infinity. And you can notice that this is the same as Kuntz algebras, that the Kuntz algebra of a simple purely infinite sister algebra is zero infinity. We actually prove that this is the case for any ordered abelian monoid, that if it is purely infinite, then it is zero infinity. So yes, this is the
wait. So the relation between so I mean, if you have any unital ring or not unital, I mean, but with the sister algebras it works. You have this monoid V of the sister algebra consisting of classes of idempotents. What's the relation between that object and the SB, at least in this Exel-Pardo case?
So in general, our type semigroup mimics the Kuntz semigroup W, and not the Kuntz semigroup CU. And in this case, let me recall, I hope I don't get this right. In this case, they all coincide, like the W and the von Neumann semigroup coincide. I hope I'm right. Am I right, Bartosz?
But so
in some cases, or in the co-final case.
There, there is this purely algebraic Kuntz semigroup of an algebra without the C star, developed by Ara and authors.
I have heard of it, but I don't know.
It would be nice to see if it were there. If it coincided with the type semigroup of the completed combinatorial algebra. Say for the Steinberg algebra in the ample case, you have the Steinberg algebra of the ample semigroup, the ample groupoid, and then you have the whatever, say, reduced sister algebra of the same thing. And well, you can compare, I don't know, all the invariants for the sister algebra and compare them with the same between, quote unquote, same invariants for the Steinberg algebra and see if they agree. I mean, certainly the von Neumann one does. I think they are the same for Exel-Pardo algebras. They surely are for Leavitt and graph algebras.
Okay. Yeah, I'm sorry. I don't know much about the algebraic picture. Yeah, I don't know how the type semigroup can be related in the algebraic picture. I'm sorry, I don't know much about this, but it is an interesting question.
Okay. So I didn't let you finish, but you were about to say that that was the last.
Yes, I was about to say that was the last.
Okay.
Yes.
Sorry.
So yes.
Thank you.
No worries. Thank you.
So are there any other questions from the audience?
But maybe just about the von Neumann and the type semigroup, the von Neumann semigroup. I think Bartosz was about to say something earlier.
I mean,
the Exel-Pardo case.
If I understood the question, because now I'm a bit confused. So the question was because there are like two different versions of a type semigroup. So one is like von Neumann semigroup, and the other one is like Kuntz semigroup. So the Kuntz semigroup is a quotient of the von Neumann semigroup. Because so here Kuntz, this type semigroup is actually partially ordered, and von Neumann kind of this type semigroup is just pre-ordered monoid. So this is a quotient. This is in general a quotient. In this picture, this is also a quotient. So this von Neumann type semigroup carries more information, And for instance, you can characterize, for instance, like Cuntz algebras with it. But here, the Cuntz semigroup kills everything. So a Cuntz semigroup of any simple, purely infinite algebra, sister algebra, is just zero infinity.
Yeah, but okay. Yeah, because the von Neumann semigroup is, I mean, the order is trivial. Everything is positive. Everything, yeah.
But what about the stably finite case?
Yes, so in the stably finite case, I think that yes, yes, they agree in a high generality.
Yes. Okay. So I'm glad I did not say something wrong. Yeah, I was saying.
Okay, so
Okay.
are there
I have a
any?
question also.
Yes, please do.
Hi,
Ask.
my question is there is a very useful characterization of purely infinite sister algebras that they are is the same as O infinity absorbing, meaning that tensor product with O infinity is the same as is isomorphic to the initial algebra. And my question is, do we have an analogous property for groupoids, and maybe if that can be also caged by the type semigroup construction?
For the groupoids, the only characterization I know of pure infiniteness of the sister algebra is locally contracting, which was defined by Anantaram and Delaroche. I don't know any other characterization, but this we do not relate this to the type semigroup, and I do not we do not have an analogous read set in the case of type semigroup here.
So I think this is a kind of a more of analytic question rather than type semigroup. So I think that in most of cases under these assumptions, you get this strong pure infiniteness, not just pure infiniteness of the sister algebra, which is known under some assumptions that is equivalent to this absorbing of O infinity. So I think that in most cases, it will be this strongly purely infinite. So yeah. So for instance, if this is, I guess Kirchberg claims that whenever sister algebra is separable nuclear, then this absorbing of O infinity is equivalent to the strong pure infiniteness. And here, these algebras will be in fact strongly purely infinite.
I actually meant when this absorption, if it can be true for groupoids, for example, we have a groupoid for O infinity, and does it happen that taking product with O infinity groupoid leaves the groupoid the same, or it's too good to be true? I don't know.
Okay. What comes to my mind is a paper by Clark, Sirakowski, Sims, and Brown, I think, where they form a twisted groupoid. Like you take one whatever groupoid and you take a twisted product with respect to the groupoid of O infinity, and they check if like when this product groupoid gives rise to a Kirchberg algebra, and this does not happen even. So yeah, in this case, if G was locally contracting, which would give a pure infinite sister algebra, then this twisted product groupoid would still give a locally contracting groupoid, which would give a purely infinite sister algebra. But if not, it's not true unless in a special setting. This
That's
is as far
interesting.
as I know about this.
Thanks for the reference. I didn't know about it.
Yeah, I think it's called purely infinite sister, like principal groupoid models for purely infinite sister algebras or something like that.
Okay, so if there are no more questions, I will stop the recording.